Okay. Welcome back to part 2 of our live session here. Again, try to attend as many of these live sessions as possible so that you can, ask questions and get additional reinforcement from others and asking questions in the chat room. But again, if you do have to miss one, go ahead and go to the video on YouTube, and you can see kind of what I'm emphasizing in these, the 3 goals for that chapter. So the emphasis on these things are core absolute knowledge you must have to understand the other things, and then going and looking at all the other different aspects of it, which are in the longer videos and in the book, will support everything that we've done here. Okay, so again, my internet is still a little hinky, so I'm going to be sharing on my computer and annotating with that. Let's see if I can do this correctly. All right. So I think we are currently sharing this. This is chapter 1, goal 3. All right. Do we see that? There. Okay. We get a thumbs up. People can see that live, right? Okay, great.
Yep.
Okay. So chapter 1 is all about bonding. And so when we started talking about shapes and bond types, we wanted to look at just the different valence electrons and the fact that we have shells. And those different shells, and most of what we're going to do is in shell 2, has an s orbital and p orbital, okay? So I'm going to talk a little bit about that and hybridization in a little different order than I had before. Let me move this over here. Okay, so when we look at this S, or when this number 2 orbital, it's the first time we're introducing the p orbitals. It's the first time we see p orbitals. Our 1s is just that spherical shape, just 2 electrons. Our number 2 is split into an S, which is the spherical, and then there's 3, the px, py, and pz. So they go in all 3 different directions, okay? If we were to bond with that, what we would see is that we would have bonds at like 90 degrees, and they would be a kind of 90 degrees apart because the P's would be bonding one way and then the S would bond a different way. But we don't see that when we look at the way things bond. When we look at methane, which is carbon with 4 hydrogens bonded to it, it's in a tetrahedral shape. Those are 109 degrees apart. Okay, so that means there must be something happening here. Okay, so what I'm going to convince you of is the fact that we're going to take the orbitals that are S and P and blend them together in different ways. Those different blendings give us different electronic structures, meaning shapes in space, but it also gives us different bonding. Okay, so the fact that we're raising the energy of the S a little bit and lowering the energy of those P's a little bit to blend them gives us a little bit of stability and gives us equal orbitals. When we have equal orbitals, it's easier to bond equally to those different things, okay? So what I'd like you to kind of focus on here is that we're in, carbon and stuff. Carbon, nitrogen, and oxygen all have these hybridizations that they have in them. And when we take the S and all 3 P's and blend all of those together, we end up with 4 equal orbitals, okay? If we only take 2 of those P's and the S, we have 3 equal orbitals plus a P. This P orbital will allow us to do a different kind of bonding called a parallel bonding or pi bonding, okay? And if we take only 1 S and 1 P and make 2 equal orbitals, we'll have 2 additional orbitals that'll bond differently. Now notice the SP, the S2, and the S3, SP3 hybridized orbitals are the ones that are going to do what we call direct overlap and give us sigma bonds. The leftover P's are going to be the one that do parallel overlap and give us the pi bonds, okay? So I'm saying all that now. Let's go one step at a time to see how that happens, okay? So when we look at just the sp3 orbitals, we're taking all 4 of those orbitals and blending them together to make 4 equal orbitals, which means it's going to bond 4 times, okay? 4 equal times, okay? When we have that sp hybridized here, we are all taking the s in 2 of those p's, meaning we're going to have 3 equal sp2 hybridized orbitals plus a p orbital. It's going to bond a different way. And when we only have 1 s and 1 p bonded to give us 2 equal orbitals, those are going to bond in a certain configuration, and we'll have 2 p orbitals left to bond in a different configuration. Okay, so in one of the notes there, the little sigma is a box and the pi is a box. So this is the correct symbols. The sigma right here is the bonds formed by direct overlap of the hybrid orbitals. Okay, sigma bonds are formed by direct overlap by the hybrid orbitals. Okay, pi bonds are parallel overlap by the p orbitals, the leftover p orbitals, meaning you can only have a pi bond when you have an unhybridized p orbital. This is a key factor, okay? So if you have all 3 p's blended with your s, you cannot have a pi bond. If you have an sp2 hybridized, you have 3 bonds to it plus something that can give you that pi bond. If you have sp2, that means you can have 2 bonds and you have 2 p orbitals that can make up to 2 pi bonds. Okay, follow these as we go through. Okay, so the next slide shows you what the different shapes are associated with. If we use this valence shell electron pair repulsion theory, we have 2 things to think about. One, where is the electron density surrounding it? And if those electrons are negatively charged, they're going to repel each other. So they're going to try to get away from each other as far as possible. Okay, so that being said, let's see if I can, not trying to like you, I'm trying to move you up so I can expand on this. There we go. All right, I'm trying to expand that up here. So if we have sp3 hybridized orbitals, that gives us 4 equal orbitals. That's 4 equal parts in space, and they want to evenly space themselves out in space, which the farthest they can spread themselves out is 109.5 degrees. That gives us a tetrahedral shape. That means anytime we see an atom that is a tetrahedral shape in electronic structure, that means it is sp3 hybridized because it has 4 equal orbitals, okay? Notice that in ammonia, right here, we only have 3 things bonded to it because it has a lone pair. It wants 3 bonds plus a lone pair. If we looked at the electron, just the electron density there, remember there's electrons between the nitrogen and the hydrogen there, it's still tetrahedral shaped in electrons. However, because there's no atom above where the lone pair is, the molecule is now pyramidal. It looks like a little pyramid on a 3 tripod here, okay? And if we look at water, that oxygen is sp3 hybridized, but it only has 2 bonds to it and 2 lone pairs. So electronically, it's still tetrahedral, but if we look at just the atoms, it is now bent, okay? So when we look at those things, the reason these are shaped this way is the electrons are sp3 hybridized, and the bonds show the molecular shape. So that's one thing that really, once you start seeing that in each of these molecules, you're going to go, aha, that makes so much sense, okay? So you have to think electrons give it the space where they are, the bonds give it the molecular structure it is. Okay, so let's talk about trigonal planar. If we take 2 of those p orbitals in the s, we have 3 equal bonds. We have 3 bonds that we can do plus a p. We're going to leave this p over here for right now. Okay, so to spread those 3 equal out as much as possible, the only way we can do that, even in 3D space, is 120 degrees apart. So anytime we have a sp2 hybridized carbon, we're going to have a trigonal planar structure, meaning they're going to be 120 degrees apart and make a plane. So if you take any of these molecules, you're going to have a flat portion on them, and so you can look straight over it, right? But remember, there's a P left over. So that P is going to be above and below that plane, and we'll get to that in a minute. So if we look at this structure here, the carbons on each of these right here are sp2 hybridized, and therefore they're trying to be 120 degrees apart. Okay, so this carbon and this carbon are sp3 hybridized, trigonal planar. I'm sorry, they're sp2 hybridized, 3 equal orbitals, trigonal planar. Notice this carbon, this oxygen here, it actually also is sp2 hybridized, forming a trigonal planar structure, and the double bond here is made by that leftover p orbital. Okay, so let's look at the last configuration here, the linear here. So in the linear here, what we typically have is an sp hybridized carbon, and they're pushed out as far as they can go. And then, so this is an sp hybridized carbon, and this is an sp hybridized carbon. But that means there's 2 p's left over on each of those carbons. So the first double bond is one of those sets of p's. The second double bond is the second set of p's. Okay. So if we look at this carbon here is actually sp hybridized. And we know this because it forms a linear structure. So the first bond, the sigma bond here, is the sp hybridized orbital. But that means that there is a p orbital available here in the x position and a p orbital in the y position here. And those are the p orbitals that are overlapping with these 2 oxygens. And you're thinking, oh, that oxygen, it was sp3 hybridized up here. It's sp2 hybridized here, right? Because it's trigonal planar, okay? But it's in a linear molecule, okay? But let's look at this oxygen. This oxygen has 2 lone pairs and a single sigma bond, and then it's pi bonded. This oxygen is still sp2 hybridized because it still has the 1p that overlaps with the carbon on one side and the 1p that overlaps with the carbon on the other side to give us our linear shape. So the carbon itself is the sp hybridized, but the oxygen is the sp2 hybridized. And of course, all of the tetrahedrals are sp3 hybridized. So tetrahedral, 4 equal bonds, trigonal planar, 3 equal bonds plus 1p, sp2 hybridized, 2 equal bonds plus 2 p's. Okay, that's the really critical factor here, okay? Questions on that real quick? All right, I'm gonna clear my writing and move to the next slide. All right, so that being said, when we, oops, not that small, look at the shape of molecules, you first think about where the electrons are, and the electrons are going to give you how evenly distributed the bonds are going to be. So if your central atom is sp3 hybridized, the electrons will be tetrahedral, but the bonds control the shape of the molecule. So in the case of carbon here, we have 4 bonds, it's tetrahedral. Nitrogen, 3 bonds plus a lone pair, pyramidal. Water, still sp3 hybridized, but it only has 2 bonds. So molecularly it's bent, but electronically it's tetrahedral. And we see that same kind of geometry change when we look at the sp2 hybridized. sp2 hybridized, 3 equivalents. They're going to try to be out 120 degrees apart. Now, if we look at it on the side, like in this one here, it's actually flat. These are spaced out as evenly as possible. And guess what? That p orbital is going to be sticking up and out of that plane, giving us our next bond. but the sp2 hybridized orbitals, those 3 equivalent orbitals, give us this trigonal planar shape. And that's seen in the ethylene here too. It's that trigonal planar shape. Notice these aren't exactly 120 degrees, and that's based on the size of the atom. Hydrogen's kind of small. Carbon's bigger than hydrogen, so it's going to push a little bit. So they're not exactly 120 degrees, but they're close to 120 degrees. And we see the same thing when we go to the carbon dioxide and the acetylene. That linear structure is made from the sp, the 2 equivalent bonds. They have to be 180 degrees apart. And then the leftover p orbitals are what give us our double and our triple bonds in the 2 compounds respectively. Okay? Questions on that? So look for the hybridization, gives you where the electrons are going to be and what the shape of the molecule is going to be. But don't forget that electron pair. That electron pair does control shape as well. Okay. So now that I have shown you that they do hybridize and that they do fill space, let's talk about how they actually change the shape of the orbital itself, okay? So when we change the shape of the orbital, it's because the P is dumbbell shaped, okay? Equal on both sides, okay? But we are blending in a little bit of S, okay? So that S is spherical, okay? So we have a dumbbell and we're adding a sphere to it, so it changes shape. We've slightly enlarged one lobe of the sp3 hybridized orbital. And when we do that, we try to get the 4 biggest lobes as far apart as possible. When we do that, that gives us our tetrahedral structure, okay? Only one side of the lobe is slightly enlarged and they spread out as much as they can. There are no P's to worry about. That's all we have to worry about is those 4 equal, slightly enlarged P-shaped orbitals, okay? Now, that means that when we do these structures here, they are spread out as much as possible. But when we have lone pairs, instead of sharing the electrons with an atom to give us our sigma bond, we just have 2 electrons in that orbital. They're still there electronically. They're still sp3 hybridized. They just take up space. They're not a bond, okay? So electronically, we are still tetrahedral. Molecularly, we've changed shape because molecular depends on the atoms we're bonded to. And the lone pair itself is just taking up space and is being repulsed, is repulsing the other electrons, okay? So sp3 always has an electronic tetrahedral shape. It's just the bonds can change the molecular shape, okay? So let's take our sp2 hybridized now, okay? So we had 2 p orbitals and we're adding s to it, okay? So that s is spherical, and so we're actually gonna change the shape of the dumbbell again. It's gonna be slightly larger on one side than the sp3 hybridized because we have more s character, okay? The s is only spread out over 3 orbitals and not 4. So it's gonna be a slightly enlarged dumbbell. And so when we try to spread those out as far as possible, we can get to this, this trigonal shape here is as much as we can spread those out in space. But remember, when we do that, we still have a P left over, okay? And that means that P is gonna come out in this Z axis. It's coming straight out of this plane and below this plane. And that's what this represents here. This represents that unshared, that unhybridized p orbital evenly distributed above and below the plane created by these 3 hybridized orbitals, okay? So that means that we can bond something here in a sigma bond, we can bond something here in a sigma bond, we can bond something here in a sigma bond, but whatever happens with this p orbital above and below the plane has to be a pi bond because it has to be, it cannot be directly shared with this hybrid orbital. It has to be shared in an overlap orbital. So what does that look like? Let's clear. what that would look like is we form our sigma bond first with our hybrid orbitals here, and hydrogen and these two carbons here. That's our sigma bond, is that hybridized orbital. And the leftover p orbitals are going to overlap above and below the plane. So those are our overlap orbitals, or our pi bonds here. So sigma bonds are hybrid orbitals, pi bonds are unhybridized p's. Okay. Okay, nothing in chat. And then we can extend that again to show it happens in this formaldehyde too. Remember, the oxygen is also sp2 hybridized, meaning it still has a pi bond. I'm sorry, it still has a p orbital above and below the plane. The p orbital on the oxygen that's unhybridized overlaps with the p orbital on the carbon that's unhybridized to give us our pi bond. So it's the oxygen itself is trigonal planar, the carbon itself is trigonal planar, and then that last p orbital on each of those atoms creates that overlapping bond, or that pi bond. Okay. So if we extend that again to sp hybridized, okay, so now you have one dumbbell shape and one spherical shape. So that means the one side of the lobe is going to be really, really big, and the other side is going to be really, really small. And since we only have two equal orbitals, they are going to spread out as far apart as they can, which is the linear. And it's going to look something like this. But we've only used up one of those p orbitals. That means that we still have a px and a pz that have to be somewhere. So the px is going to be outside the plane of the hybridized orbitals, but the pz is going to be in the plane with the hybridizers, but at 90 degrees away from it, because that's as far as we can get. So the hybridized orbitals are 180 degrees apart, but the p orbitals are going to be 90 degrees from each other and 90 degrees from the sp hybridized orbital. So that gives us a linear bond here and two different p's that can form up to two pi bonds. So what does that look like when we have the acetylene? When we have the acetylene, the sp is the sigma bond. The first p orbital that overlaps is our first pi bond, and the second p orbital that overlaps is our second pi bond. Okay? So, what if this was the CO2? I want you to take this concept and figure out, okay, I have a carbon with two pi orbitals, and I have those two oxygens, and I want you to go ahead and draw on a piece of paper later to try to figure out where those p, or why those pi orbitals, why those pi bonds on the CO2 still form a linear molecule. I think you'll find it very interesting if you figure that out. Okay, so going back to the hybrid orbitals, okay, if we have sp3, 4 equal orbitals, 4 bonds, okay, or at least 4 areas of electrons. So when we have it on carbon, we typically have 4 equal bonds, okay. If we have sp2 hybridized, we typically have trigonal planar, we have 3 bonds plus a pi bond, okay. So 3 sigma bonds plus 1 pi bond. If our carbon is sp2 hybridized, we have 1 sigma bond to the molecule, 1 sigma bond to each atom on either side, so a total of 2 sigma bonds, and then a total of 2 pi bonds available, like in acetylene, okay? So that is how orbitals hybridize and why our molecules have different shapes with different hybridization, okay? Let's see. Yes, okay, to answer the group chat there, sorry, I didn't see that. To be clear, the orbitals are the actual phrase is the statistical probability is where they will be in space, okay? So because the electron's moving around so fast and it's very small, is that at any point in time, it will be somewhere in that location, okay? 90% of the time, okay? So that's what really an orbital is. It's you know, at any moment in time, it will be somewhere in that space, and it has a negative charge in it. So it's repulsing things somewhere out of that space. So that's why it takes up there. Do we know when the angles of the molecule will change depending on the amount of the bonds? For example, trigonal planar is usually all 120 degrees, but some models differ. Okay. If they were all equal and all of the atoms were the same size, they should all be the same angle, okay? The only time we see that change in angle size, like in formaldehyde, is that the oxygen is bigger than the hydrogens, right? Because it has other electrons on it. So the bigger the atom gets, the more it pushes it out of that ideal 120 degrees. So anytime you have a slightly larger atom, you're going to have a slightly bigger angle next to it. But if they were all the same size, they should be all the same angle. Does that answer your question, Michelle? Can't see everybody. But,
yes.
Okay.
I was just curious, will we have to calculate something like that on the test so that I can figure out how to do that?
No, you do not have to have the exact a bond angle. The idea is that you want to know that they're approximately these angles. We will not be calculating bond angles. It's just helping you decide the shape of the molecule.
Okay, thank you.
Okay? Because the shape of the molecule ties into our next slide, which is polarity. Okay? So when we have polar and non-polar molecules, we have to go back to the idea that bonds can be polar or non-polar, right? We have a polar bond when one atom has a different electronegativity than the atom next to it, okay? So that's just the bond. Electronegativity tells us about an individual bond, okay? Now, whether or not the molecule is polar depends on its shape and the electronegativity of each of the atoms that it is bonded to. So for example, in CO2, oxygen is more electronegative than carbon, therefore it is going to pull from the carbon to the oxygen, giving us this polarized bond, okay? But in the case of carbon dioxide, we have equal and opposite things pulling on it, meaning that that becomes a non-polar molecule, okay? sp hybridized tells us it's a linear bond. Our electronegativities tell us that they're polar bonds. So our sp tells us that we have equal and opposite bonds, and therefore our electronegativities cancel each other out, giving us a non-polar molecule, okay? So we're adding hybridization, shape, and electronegativity together to tell us whether we have a polar or non-polar molecule, okay? Let's do that with a different shape. Let's do that with water, okay? Electronically, it is tetrahedral, okay? But there is no bond polarity between the electrons that are not bonding. So we only look at the polarity of the electrons that are bonding. And oxygen is more electronegative than hydrogen. Therefore, they are being pulled, the electrons are being pulled in the direction of the oxygen here, okay? Now, because it's sp3 hybridized, we know that angle is about 109 degrees, which means they're not being pulled in equal and opposite directions. That means there's at least the one that's being pulled in this direction here cancels the part of the thing that pulls it in this direction here, but that still leaves, both of these have an up component, okay? The ones that are pulling toward each other, these will cancel out, but these that are pulling in that up range add together to give us a net polarity in this direction. So our sp3 hybridized system with only two bonds, so we have two polar bonds and they are not equal and opposite, therefore they do have direction, therefore we have a polar molecule, even though if we had carbon with 4 hydrogens around it, we would have a non-polar molecule, okay? So molecular shape, hybridization, and polarity of bonds, all three must be considered when we look at the polarity of a molecule in itself, okay? So let's add another component to that. let's change the shape again. And so now we have a pyramidal shape here. Now we have to look at the polarity of each of these bonds with the hydrogen and the nitrogen. The nitrogen is more electronegative, so it's going to be pulling electron density. And if we look from the top, we have equal directions being pulled toward that nitrogen as far as this, X component goes, but we still have a bunch of different components here that are all pointing in the same direction. That means the part that's pointing in all three directions, those cancel out because they're all pointing together. But they each have an up component too, because this is at an angle. So all of those up components are aligned, and therefore we have a net polarity of the molecule in that direction. Hybridization is still sp3, but the polarity of those three bonds have a component that goes in the same direction. Therefore, we have a polar molecule. Okay. And let's look at our last one right here. Okay. So if we look at this one right here, this chloromethane, if we replace this chlorine with a hydrogen, we have no polar bonds, and they're all in equal and opposite directions. Therefore, it would be a non-polar molecule. Okay, by replacing one of the hydrogens with a chlorine, we now have a more electronegative atom pulling it in this direction. These are basically non-polar bonds, so they don't contribute any component, and therefore the net is that the molecule has a dipole here. Okay, so let's look at formaldehyde. Okay, this is an sp2 hybridized carbon, meaning it's flat, right? It's planar. Okay, however, we have a more electronegative atom on this side than on these sides. The hydrogens barely have any contributor to all. It's almost a nonpolar bond. But even though this is a trigonal planar, it is pulled in this direction, and therefore is a polar molecule. Okay. Now we have a nonpolar bond and nonpolar, this is a nonpolar center bond here because carbon and carbon are the same. Carbon is ever so slightly more electronegative than hydrogen, so it slightly pulls here. But because it's sp hybridized, those are being pulled in equal and opposite directions, and therefore it makes it non-polar. Okay, so that being said, when we look at total polarity of a molecule, hybridization gives us where the different the bonds go in which direction. The electronegativity difference between the two atoms tells us which way the arrow is going, and the total of all the different arrows tells you whether or not it's a polar or non-polar molecule. Okay, so sure. There we go. So in summary of this section, goal number 3, S and P orbital hybridize to give us energy. When they hybridize, they give us different shapes. So sp is a different shape than an sp2, which is different than an sp3. Okay. You have to remember the electron pairs when looking at molecular geometry. Okay, because those electron pairs take up space and repel other electrons. Okay. The sp hybridized orbitals are the ones that make the sigma bonds. Okay. They either make a sigma bond or they're a lone pair. Okay. Only the unhybridized p orbitals make pi bonds. Okay. If we get those things kind of in our head, every time we look at a molecule, we say, oh, that's sp2 hybridized, it must have a p, that p must be making the pi bond. That means we can do something with it. Oh, this is an oxygen, this is a carbon, meaning there's a polar bond there. That's probably something we'll need to take care of, or we'll have to pay attention to. So by just adding these rules kind of every time we look at a molecule for the first few days, you'll start to see a pattern emerge, and you'll start to say, hey, that's a polar bond. I bet that's going to be where some of the reactions might happen. So that's why these are so important as a goal for our chapter 1. Okay, so I'm going to stop sharing here and go ahead and open it up for questions. I know we hit right at 1:40 here, but if you have any questions or want to stay behind, let's see, is the homework on Top Hat yet? It will be on Top Hat by 5 p.m. today. So homework will be on Top Hat by 5. So any other questions in chat, or anybody want to chime in? Okay, your time is valuable. My time is valuable. We're right here at 1:40. I'm hoping I'm ending pretty much on time, even with technical difficulties. We will continue with chapter 2 goals tomorrow, and we should get caught up on part of chapter 3 goals as well. Okay, all of chapter 2 videos will be uploaded here in just a little bit. All of chapter 2 videos will be uploaded by 5. All of chapter 3 videos will be uploaded by midnight. Okay. All right, I'm going to stop recording so we can have this posted to the internet. And if you want to hang around and ask a question, I will be available. Stop.